Hello everybody. In this video I'm going to give you some supplemental instruction for completing our Labflow report this week, Voltaic Cells. The first thing you're going to do is you're going to get some pictures and you're going to input some values. They're pretty easy. You get a little digital display that you have to use. Then it will populate this table with our data. And then we get to this table where we're going to start to fill in our calculated values. I think the easiest way to show you guys how to do these is going to be by just going through one of the examples. I'm going to actually start with number 2 here because it doesn't have equal concentrations of zinc and copper. Just the way that they chose these, I kind of almost missed that myself at first. For instance, this one's 1 molar, this one's 1 molar and 0.1 molar. So that's going to affect how we do our calculations here. So the first thing we do is we start with this cell notation right here. And we're going to recognize that we start with the anode on the left-hand side and the cathode on the right-hand side. If we write out the reaction for this cell notation, we're going to start with the solid anode on this side. It's going to mix with the cathode ion, and then it's going to produce aqueous anode material and the solid cathode. So in this case, we're dealing with zinc and copper. Next thing we want to do is get the half cell potential reactions for copper and zinc, and we're going to label them whether they're the cathode or the anode. We're going to get these values this time not from the back of our book, but instead from this table here that's in the PDF. So I just recorded those values for the copper and the zinc. Again, I'm labeling them whether they are the cathode or the anode. The next thing I need to do is calculate E cell. So that's going to be the cathode reduction potential minus the anode reduction potential. So that's minus a negative here in this case. They're going to add together and we get 1.10 volts. I like to do that first as opposed to calculating the reaction quotient. I went here and calculated this value first because what that's going to do is allow us to have a little sanity check here. We want to make sure that we're getting a positive value here. This indicates that the reaction as we have written it up here is spontaneous. Okay, and that's what we want. So we know that we're on the right track now. From there, we can calculate the Q value. Remember that we are not going to include any of the solid phase things in our reaction quotient, and it's going to be the products over the reactants. So in this case, we're going to have the concentration of the zinc ions over the concentration of the copper ions, and that's where these concentration differences in the cell notation came into play. Okay, so we're going to plug in 0.01 for copper and 1 molar for zinc. We plug in those values to get 1 over 0.1. The molarity unit is going to cancel, and we get a unitless quantity of 10. We would enter that right in here. And we would get 10. The next thing is to calculate the E cell from the standard cell potential. So we're not at a non-equilibrium state, right? Because we're not at 1 molar for all of them. Okay. If we were at at 1 molar for both of these, then we would get 1 mole over 1 mole, and this whole term here would become 0 when we took the log. Okay. Also, in the PDF, they have a different equation that they're using for E cell. We can take a look at that real quick. They're using this equation right here. But we know from the lecture I explained to you that you could also just use this equation here, where we take all those other values and we just jam them together to get that value right there. I find that for this particular application, this equation's a little easier, so that's the one that I've chosen to use. What we have to do is we have to plug in N. Okay? If we look at our reaction and our half cell reactions, we can see that we're transferring 2 electrons. Right? We're going from a neutral state to a +2 state. We're going from a +2 state to a neutral state. So I will plug into here the 2 for the 2 moles of electrons being transferred. In my case here, I chose to just recognize that the log of 10 is 1 to make my calculation go easier, but you could just put this whole thing into a calculator if you chose to. And I got out 1.070 volts. And I would enter that right here at E cell calculated. That's going to be 1.070. And that's it. You're just going to go down this table and do the exact same thing for all these other ones. Remember that you're going to come here and use this table to get your reduction potentials. And then after doing that, you're going to answer a few questions. Using my methodology here, these questions actually become fairly easy. For instance, identify the complete redox reaction for this guy right here, the one that we just did. Well, we already wrote that out. So we know that it is this reaction right here, and that it is correct as written. And that's pretty much it. After that, you're just going to upload pictures of your work and your notebook pages, and you can submit.